Okay, happy day and welcome. We are talking about gas laws today. And so we are going to take a look at some of the gas law features and our gas law notes. All right. So, we're going to be talking about this. We've got the kinetic molecular theory, explaining gas pressure, using Dalton's law, calculating partial pressure, which you already started doing, using the combined gas law, the ideal, and then Graham's law of diffusion. And then the last thing is actually, and then using gas stoichiometry. And the last thing is just talking about what a real gas is. Most of this is review, I would say, so it should go pretty quickly. So we know that matter exists in three phases. What are those three phases? Solid, liquid, and gas. Perfect. Solid, liquid, and gas. And although, you know that in a chemical equation, they're obviously written with parentheses around them. Although few substances exist naturally in the gas state, we live in a gaseous solution that affects our lives every day. So if we look at a periodic table, we know that in red, those are going to be the gases. So yeah, we can see hydrogen, nitrogen, oxygen, fluorine. The noble gases obviously are going to exist as gases at room temperature, but most of the elements are what phase? Most of them are solids. Okay, most of them are going to be solids. Air is made up of a mixture of mostly what gas? Anybody remember this? Yes, nitrogen gas. You need to make sure that you know this. That's really important, that it's not oxygen gas, it's nitrogen. Although what supports animal life is inhaling what? Is inhaling oxygen. You can't, we'll talk about the percentages in a little bit too. You can't see most gases. They really play an important role in our everyday lives. Natural gas, which is methane, and we know that methane is what formula? Remember Mary Eve? Yep, CH4, perfect. So that's just one carbon and it's got the 4 hydrogens go around it that are going around it. It's used as an energy source for heating, electricity, fuel, and in the production of organic materials. It says the atmosphere is immersed in waste as industrial processes release pollution into the air, creating smog and acid rain. So they release these gases, and these gases end up reacting with what up in the atmosphere? With what is up there? Or just simply what, when you look up into the sky and it's not, doesn't necessarily need to be a sunny day, what's there? Clouds. Perfect. And we know that the clouds are simply made of what? Of the water. Okay. And so then what ends up happening is they react with the water, and then that's how the acid rain can form. A common gaseous product of burning fossil fuels that's causing global warming is blank. CO2. The same gas, CO2, is used to blank soft drinks. Carbonates. Very good. So you know that we say that CO3 is called carbonate, right? So just with one more oxygen. So they use carbon dioxide to carbonate. In this chapter, we're going to study the properties of gases and the laws, and then why they behave the way that they do. Okay. So it says a few properties of gases that should be reviewed. Okay. So if we take a look at this PhET simulation here, we can see that the molecules are bouncing against each other. This is according to what is called the kinetic molecular theory. Okay. Are they stopping? No. Is there a battery? No. Are we adding any heat? No, we're not doing any of the above. These molecules are simply going to bounce off of each other. Now, I want you to kind of see if you can pay attention to one, if you can, and notice the speed of them, okay? So I want you to take a look. Do they all have the same exact speed? No. No, they don't, okay? But on average, we can say that they contain an average speed. But what happens is you get one that's faster and it hits one that's moving slower, and what happens? It can transfer energy. Awesome. And so there's always this like transfer of energy from one molecule to another. And so we know that from the law of thermodynamics, we know that energy is always conserved. It's always conserved. It's always going to be constant. Okay. So when we cool it down and we go into the liquid phase, the molecules are going to get closer together. And then obviously in the solid state, they're going to get even closer. And then what did we say when we did bonding in Vesper? So in the solid state, they take on what types of structures typically? crystal structures. Okay, even if it's so we're going to talk about crystallization of the solids when we do intermolecular forces in one of the next units as well. Okay. Now, water, just so you know, because it is nice to see in the gas phase, it behaves the same way. So whether it's a molecule or single atoms like neon was, that they're just going to bounce off of each other, and same thing is going to happen. They're going to take the entire size of the container when they're in the gas state. So they are hitting up against the sides. And so if I made this container bigger, then what would the volume of the container be? What would the volume of the container be if I made the container bigger? It would be, I'm sorry, the volume of the gas will be the same as the size of the container. So the volume of the gas is always the size of the container. I didn't add any. So if I did shrink this, made it bigger, you're not adding any molecules to it. The number of molecules are the same, but your volume can increase and your volume can decrease. Okay. And when you do that, you can change the pressure. So I'm not changing the moles if I were to do something like that. The cool thing about water is you go into the liquid state and it looks like that. Anybody know what's funny about the solid state with water? And we'll talk about this when we do solutions too. Yeah, it actually becomes less. Yes, very good. It becomes less dense. There's more air in between, which is why if you drop solid ice into liquid water, what happens? It floats. Okay. Typically, solids are going to sink in their own liquid. Almost every other solid will sink in its own liquid. But with water, it does things a little bit different. Okay, but we're just talking about gases now anyway, but good to see how the liquids and the solids behave as well. Okay, so gases assume both the blank and the blank of their container. Shape and volume, perfect. Shape and volume of their container, and they expand spontaneously to fill their container. Gases are blank. When pressure is added, they become smaller. What is very good? Compressible. They are compressible. Okay, and gases flow readily and blank rapidly. There's a word that starts with a D. Very good. Diffuse. They diffuse rapidly. Okay, gas pressure. So if I were to ask you what the equation is for pressure, okay? So I want you to think about somebody adding pressure on you. So if somebody added pressure on you, what would they be doing? Possibly doing what? Pushing. Okay, so there's a certain amount of, I like it, there's a certain amount of force that's being applied per unit area. Okay, so I remember there was a show and it was one of those like extreme something shows, and the people had to run across this, like, it was like rocks and broken glass, and they were like, how do you do this? And then like there was always like the one person that was like, so what I'm gonna do is I'm just going to like really fast, I'm gonna run as fast as I can, and I'm gonna use like on my tiptoes, I'm just gonna tiptoe across that whole thing. And then you get the person that's like, so what I'm gonna do is I am going to try to use as much of my foot as I possibly can in order to get across. I may be slower, but I'm going to use as much of my foot as I can. Which one's going to be right? The tiptoer or the person using more of their foot? More of their foot. Why? Because you're increasing the surface area. Okay. So what is pressure? It is the force per unit area. Which, so if we say like tires, anybody have to fill their tires? And what do they say? They ask you how many what you want to fill, right? Do you guys remember the units? PSI. So like PSI, what does PSI stand for? Pounds per square inch. So this is pounds. Well, I'm just going to do it as, let's just do it as a unit. So it's pounds per inch squared. That's what that is, right? So what we're going to say is it's how much are you applying per area. Okay, so when we say PSI, the SI unit is called the Pascal or the kilopascal, which is funny because they don't show that on the AP equation sheet. They don't. That's like the one unit that they don't give you. And at sea level, anybody remember what 1 atmosphere is equal to? How many kilopascals? We can start with that one. 101.3, I like it. 101.3 kilopascals. And what about what's the other one that we use? Torr, which is the same thing as millimeters of mercury. And what's that one? 760 millimeters of mercury, which is the same thing as a Tor, named after Torricelli. Okay. Okay. So we've got these like sea level units. And it says if you need to convert, you just set up a bridge. We did that when we were looking at like the Dalton's law stuff, if you're trying to switch. What's empty space with no particles and no pressure called? Vacuum. A vacuum. To use in the word vacuum. And atmospheric pressure is the pressure from collisions of what? So if it's, but three-letter word, pretty easy, air. So it's the collisions of the air molecules with other objects. Perfect. Okay. Is pressure higher or lower as you travel up in the atmosphere? We already talked about this. It is lower. So the air pressure is going to be lower. We said why? Due to gravity. Due to gravity, the air molecules are pulled. Air molecules, I'm going to abbreviate molecules, MOLC, are pulled toward the center of the earth. And so everything gets pulled down. You're playing a game of hockey on Orchard Lake and the ice beneath you starts to crack. What should you do?
Just don't land yourself.
Yes, don't start jumping around, don't start bouncing around, don't get on your tiptoes, right? So instead what you want to do is you want to spread out. Spread out. Okay, so let's see why. Okay, so we already said what the equation was. P is equal to what over what? F over A, right? So as your denominator gets bigger, if you increase this and you make your area bigger, what happens to your pressure? Then the pressure goes down. So we know that mathematically, if you can increase your denominator, keeping your force the same, right? So you could do that. If you could decrease. So let's say you've got skates on, but really in order to take your skates off, it's going to take a second, right? So to decrease that is going to take a little bit. The ice starts to crack, you're having pressure. So the better thing to do is to increase your area. And then that means that your pressure decreases. So when you increase your area, you decrease your pressure. And so then hopefully you don't have an accident. Somebody can pull you off or something, or you can kind of do a crawl or something like that to get off. Okay. Instruments used to measure pressure, barometers and manometers. Okay. So barometers, this was constructed by Torricelli, who was a student of Galileo. And so it's very, very simple. The reason why we can't have barometers, so like when I went to state, we did have a barometer in our lab area. And the reason why we can't is because it's open to the environment. Let's see, what's in it? Mercury. There's mercury inside of here. And so what happens is, as the air pressure increases, it pushes on the mercury in here. And then where does the mercury go? The mercury pushes up. So the more pressure you add on the outside, the greater the air pressure, then you could see that this column, the mercury inside, would actually rise and fall. The nice thing about mercury, it does vaporize, but not as Riley said, as volatile as a lot of the other gases. So like if we use alcohol, the alcohol is going to vaporize really quickly. So it has to be a closed system. So it's harder to get something like that. Okay, manometers. These measure gas pressure. There are two types. So there's an open end and there's a closed end. The closed end is vacuum sealed. Okay. What does that mean again? It means that we've tried to get rid of everything else, right? So just trying to create a vacuum where we try to get rid of any of the air. Okay. So the closed end is easier. When you look at a closed end manometer, we just say that the pressure of the gas is equal to the pressure difference. It's pretty simple. So since it's vacuum sealed, the atmospheric pressure is not going to affect the manometer. This is really important. Atmospheric pressure doesn't affect it. You can be given a closed end manometer, and what people will do, they'll make a mistake and they'll give you the atmospheric pressure and they'll try to include that in their calculation. Don't use it. Okay. If it's a closed end manometer, your pressure of your gas is whatever the difference is between the two sides. Okay. So it says the pressure of the atmosphere is 104 kPa. But guess what? If it's a closed end, what are we going to do? Ignore it. Don't use it. Okay, cross it off, don't use that. And the difference between the two sides is 215 millimeters. What is the pressure of the gas? I think I added, I don't know why I have two different pressure of the atmosphere, but the pressure of the atmosphere doesn't matter anyway. We don't care about the pressure of the atmosphere, okay? So what's the pressure of the gas? So it is 215 millimeters. The only thing that they could do differently is say, what's the pressure of the gas in, let's do kilopascals, okay? So instead, we're gonna do it in kilopascals. So I'm gonna say 215 millimeters of mercury. And now I've got my millimeters of mercury down here, and I'm trying to get to KPA. Okay. So what's the easiest thing to do? What are our two numbers for this? KPA is, yep, 760 for millimeters of mercury, and KPA, 101.3 KPA. And so all we're gonna do is multiply and divide this. I have a calculator here. 215 times 101.3 divided by 760.
It's approximately 28.657.
So 28.7 is what we're getting. That sounds right. And then that would be in KPA. So that would probably be the hardest that closed end manometer would get, is just switching to a different unit. Okay, open end manometers on the other hand. So if it's open, then the pressure of your gas, you need to know what the atmospheric pressure is, and then you're either going to add or you're going to subtract the pressure difference. So you're going to take the atmosphere and then add or subtract. How do you know if you're going to add or subtract? If the pressure of the gas is greater, and so some people will memorize, like if it's higher on the right or lower on the left or whatever, you really just want to think about, if the pressure of the atmosphere is greater than the pressure of the gas should be less, right? So what would you do if it's less? You would subtract, okay? If the pressure of the gas is greater than the pressure of the atmosphere, then we should add. It's pretty easy, okay? So you need the atmospheric pressure for sure, and then you're either going to add or you're going to subtract. So if the gas is coming in this way, and it's pushing against there, okay, we're going to take a look at both sides, because if they're equal to each other, what should be true of the level of the mercury on the inside? The level should be the same. They should be equal to each other. So if they're not equal, that would be in equilibrium with each other. Then you would say there's no difference between the two sides. The pressure of my gas is the same as the pressure of the atmosphere. And so your difference is zero, okay? So if it's an open end manometer, then what we're going to do is we're going to check to see what the difference is between them, and then we can figure this out. So let's see what the problem says. Okay, what is the pressure of the gas in each example? So the pressure of the atmosphere is 750 millimeters. So that's our PATM. And the difference is 118 millimeters. Okay, so let's do A, which is going to be this one on the left, and then we'll do B. Okay, so the pressure of my gas is equal to the pressure of my atmosphere plus or minus, and we're going to circle one of them, the pressure difference. And you won't have to rewrite the equation just because we're doing this for the first time on here. Okay, so what is the pressure of my atmosphere? It's equal to 750 millimeters of mercury. Okay, and the question is, are we going to add or are we going to subtract? So if it looks like this, who's winning? Is the atmosphere coming on this side? Is the atmosphere pushing down more, or is the gas pushing down more? Atmosphere is pushing down more. So that means that the gas should be less. And if the gas is less, we subtract. Awesome. So then we're going to do a subtraction because the gas is less, and we're going to subtract 118 millimeters of mercury, which is going to give us 756, 632. Thank you. 632 millimeters of mercury. And again, you can switch it if you need to. Okay. Okay, and B, it says, up a little bit. Okay, so in B, we've got 104 kPa, and the difference is 215 millimeters between the two sides. But now, obviously, we can see that the gas pressure is more. And so they might say something like the mercury on the column of mercury on the atmospheric side, or the side that's open to the atmosphere, is higher. So they're gonna say it in words, they're not gonna give you a picture, okay? So if that's higher on this side, that means that the gas must be pushing down more, okay? So it almost works like a seesaw, like if it's heavier, it's gonna push down more, and then the other side's gonna come up, since this should be constant. Okay, so now we've got 104 kPa. Oh, okay, so now we know the gas is more, so we're going to add, okay, but what's the problem? It's in millimeters, perfect. So first, we need to convert our millimeters into kPa, or the other way around, depending on what they wanted. So again, millimeters of mercury into kPa. And again, we said it was 101.3 and 760. 215 times 101.3 divided by 760.
It's approximately 20.
Oh, is that exactly the same? 28.7? 28.7 kPa. And so now we're just going to add the 28.7 kPa to this. And what do we get as our pressure? Oh, 132.7. Thank you. 132.7 kPa. Okay, and that's a great intro to manometers and gas pressure. Happy day, everybody.